Welcome to part 3 and the final part of our little videos on gravitation. And here we're going to be talking about orbits. It's appropriate as we're talking about orbits. We've got a little simulation here of planet Earth moving in an orbit around a yellow blob that we're going to pretend is the sun, although this is of course not to scale. And additionally, we're going to be talking about orbits as though they're circular. As you can tell here, hopefully, this is not a circular orbit. It looks circular, it looks really circular, except this is the center. And if we're starting off 2 squares over from the center, bloop, right there, we should have 2 squares in all directions. If this is a radius, they should have the same radius everywhere. So if this is a circle, it's not centered about the center of the sun. And if it's not centered around the center of the sun, it's most likely an ellipse. And as you can tell also that it is a little bit, the height here is a little over 2 squares in both directions, but it's definitely more than that off to the side. So we're dealing with something that's elliptical, but it's pretty darn close to circle. And since it's pretty darn close to circular, that means we're going to be able to use circular motion to help us figure out exactly how fast an object would need to go if it was going to stay in orbit around a star. In this case, the centripetal force that makes this thing go in what, again, we're approximating as a circular orbit, the centripetal force is being provided by gravity. So that means the gravitational force is a centripetal force. Let's take a look at the notes. We've looked at centripetal forces being caused by normal forces, tension forces, friction forces. Technically, we could even do it just with gravitational force as in terms of m times g. But in this case, we want to take a look at centripetal force equaling the gravitational force or being provided by the gravitational force in terms of the new gravitational force equation. And just to make sure that we're not missing anything here, this is okay in terms of direction. So if we have a sun in the middle, and we've got a circular path going around that sun and a planet, it has a tangential velocity like so, like we had in the picture. It should have a centripetal force directing it towards the center, but the gravitational force is also towards the center. The force due to gravity acts towards the center of the circular path, and the net force on an object making it go in a circle is called the centripetal force. So even if we were to attach signs here in terms of direction, they'd be going the same direction. One's not going to be negative of the other. So since the force due to gravity is negative of the positive radius direction, that means it's going towards the center of the circle, and so is the centripetal force. So they're the same sign. We can say that they're just going to be equivalent to each other. If we do that, we have a very specific velocity that allows an object to go in a circular orbit or approximately circular orbit. And that would be square root gm over r. Now I typically tell people they can memorize this by it being a radical symbol. You know, square root is radical. And gm over r looks kind of like gamer, GMR, gamer. So going into orbit like a rad gamer is one way to remember this. So, you know, if you got your Twitch stream is on fire and you're getting all sorts of subscriptions and tips or whatever the heck goes on in that world, I really don't. I'm just making it up as I go here. If you're a rad gamer, you're going to be going to orbit in your moon Lambo or something. Anywho, rad gamer is going into orbit. So what's kind of funny about this is that's the specific velocity required to go in a circular orbit. But if you note, it's not too far off from what it takes just to get lost forever. So staying in orbit's a tricky business. If you're a little too fast in orbit, you're going to go off pretty far. So in fact, if you go square root of 2 multiple of the velocity to go into circular orbit, you just never come back. You go bye-bye. So let's take a look back at that simulation here, where we're going in pretty much a circular orbit. If I increase that velocity, I'm going too fast for the force here. Now, if you're going too fast for, say, the frictional force that makes you go in a circle in your car, you skid off. You go beyond the arc of your turn. You go off the side of the road. Same thing happens here. The planet's going too fast, it goes beyond this path it was supposed to go on, except it still has some sort of force acting on it, so it will come back. It will return to its original position, but it's definitely not going in a circle now. As it moves further away, it goes beyond where we wanted it to go, the force of gravity decreases, but it's still pulling on it and it's still able to change its direction and try to slow it down. At about this point, you can see that the force of gravity going towards the center, what would hopefully have been a circular path, is now not just changing the direction of the velocity, but it's also kind of acting with it, because we're not at 90 degrees anymore. It's actually speeding up the object. So it goes faster as it gets closer, and then as it goes off track, it's got too much momentum, continues on, and there you can see the force of gravity actually acting a little bit against the velocity, so it will slow down. Now, as this comes back around, we can see what happens if we decrease the velocity. Now it's going way too slow for the path that it normally was traveling on, and it might hit the planet. Oh, it doesn't. It actually makes it around. This you can definitely tell is an elliptical orbit. Now, we don't really want an elliptical orbit, so let's go back to the original, and where it looks like it's going pretty much circular. But what happens if we just, this is let's say this is a length of 1. Put the grid on there. We want to go about 1.4. So if we go to right here, 1.5, 50% more. At this point, the object should never return. It should just go bye-bye. So let's see what happens. Force of gravity is still acting on it, trying to slow it down, but that velocity is just so big that that acceleration of gravity that drops off of the inverse square distance is just never going to be enough. If you drop a little bit underneath that, it's going to go pretty far, but it should theoretically return. You can see it's definitely turning more, but either way, it's not in a circular orbit. So there's this very, very particular velocity that if you start off with it, you will go in a nice circular orbit, or as close to circle as we can get. Go too fast, you go beyond a circle and make a big ellipse. You go too slow, you make a small ellipse. Now, what if we were to take a look at, instead of the specific numbers, although we can calculate that for the planet Earth. In fact, why not? Let's open up the calculator here. Let's get crazy. If I put in the g value, I'm sorry, we'll do square root first. Square root of 6.67 times 10 to the negative 11th. We multiply it by the mass of Earth, approximately 6 times 10 to the 24th. And we divide that by the radius of the Earth, 6.4 times 10 to the 6th. Now, this is if we were at the surface of the Earth, how fast would we need to go in orbit? We would need to go almost 8,000 meters per second in velocity. That's a lot. Okay, that's a lot. What if we were at the height of the International Space Station, where instead of having the 6.4, we're roughly about 6.8 times 10 to the 6th? It's still got to go pretty quick. We're not going to be going slow and making it around in orbit around the Earth. So you got to go really fast. In order to go in a circular orbit way, way beyond that geosynchronous orbit, we could calculate those as well. We just have to put in a new radius value. But let's go ahead and take a look at what would be needed if we were on a planet Earth with radius capital R as Earth's radius, and we had a satellite that was in orbit around a planet with mass 2 times that of Earth. So it's at it's orbital radius capital R. And now we go to a planet that has twice the mass. What orbital radius would the satellite need to be at to maintain the same velocity? So this satellite doesn't handle moving too quickly, let's say. So if we were to double the mass of the planet, what would we have to do to the radius of orbit in order to keep it the same? It should be pretty obvious that it would just be twice the radius. In this case, we're not doing anything crazy mathematically. The old velocity was just equal to square root gm over r, rad gamer. And we wanted to have twice the mass. We want to keep the same velocity. So the question is, what goes into that spot next to the r in order to make nothing change? Well, hopefully your algebra skills are pretty good and you notice that would just be r. Now, we could also do some comparisons, say, well, what if we doubled the mass and tripled the radius, and then we'd have to have like square root of 2/3 and weird stuff like that. Didn't really want to put into a problem, but problems like this are kind of common comparative problems where you have to do factoring. Now, in terms of something going in orbit and having this elliptical path, one of the big questions is, well, like, is it predictable? Like, how do we know when it's at a particular place, how fast it's going to go? And the answer to that is conservation of angular momentum. Whenever you have a closed system, momentum is conserved during interactions. Angular momentum as well for collisions is that case. If you're really a calculator. But if you have an object that's going through orbit, and we say there's no air resistance acting on it, it's pulling on the sun and the sun's pulling on it. They're a closed system, which means angular momentum should be conserved at all times. You can think of this as a figure skater who's going around and pulls their mass in order to lower the rotational inertia, which for the case of a point mass, the rotational inertia is equal to m times r squared. If you were to make this radius smaller, like a figure skater does when they pull in their arms or legs, that means that you would want to have an omega go up. Remembering our angular momentum is I times omega. So if rotational inertia drops, the omega would have to increase. And omega being a factor of tangential velocity, the tangential velocity would have to go up. So as a planet goes into orbit, if it's an elliptical orbit, in this very, very exaggerated orbit, as it's far away from the sun, it's going to go slower. But once it starts moving in, the acceleration of gravity is going to pull on it. That acceleration of gravity increases, so we got a little bit of acceleration of gravity there. If it gets to a point, say right here, it's going to have a velocity that's increased, and the acceleration of gravity is going to get bigger. And then when it gets around to this smallest radius, it's going to have a really big acceleration of gravity, but it's also going to have a larger velocity. So that's when it kind of whips and slingshots around. But conservation of angular momentum, mvr for a point mass, is going to be the same at all locations along this path. Now lastly, and this is kind of a whammy extra one, this is coming from Kepler's laws, which say, basically what we stated here, that the period of orbit is related, not directly, but related to the radius that an object is at. Now, that seems to kind of make sense that the farther out you go, the more time it's going to take you to go around. And we can see that from if you're going in an orbit, the farther out you are, you should have a lower speed. And if you have a lower speed and you're going along a bigger distance, it should take you longer, right? So if we connect this idea of orbital velocity with this idea of a tangential velocity of a circular path, again, we're assuming a circular path here, but it's still, the idea still holds for ellipses as well, where tangential velocity would be 2 pi r, the circumference divided by capital T, the period. Then we can combine these two, we can set them equal to each other, do a whole bunch of algebra, all right, algebra cadabra, poof, and we get this expression right here. Not pretty, all right, but the big idea is that it's not a 1-to-1, okay? The period squared is going to be proportional to radius cubed. And if you wanted to get really fancy with it, you could say that the period of orbit is going to be, sorry, I forgot to do the little squiggly thingy, is going to be proportional to 3/2 power of the radius. So if you double the radius, you're not going to get double the period. You're going to get a little bit more than that. If you triple the radius, you're not going to get triple the period. You're going to get a 3/2 power of tripling it. So it's going to be a little off, but in fact, I don't even know what that is. What is 3/2 power for, say we double the radius? What's that to the 1.5 power? Ooh, 2.8. All right. So you're getting, if we divide that by 2, we're getting like a 41% increase. So it's like a rad 2 thing. That's kind of crazy. If you tripled the radius, you'd have 5.196, which is radical 3. Oh my goodness, are we good? Oh yeah, I think I see what's happening here. So again, this is not a very commonly used formula for putting numbers into it, but this idea that the square of the period is related to the cube of the radius is important. And that's where we're going to end this gravitational stuff. We'll look at some review problems in class.